Okay, so today we're going to talk about what a limit is and two different ways to find them. We're going to talk about how to find a limit graphically and then numerically. So first to start off, let's talk about what is a limit. So now on your screen, there's this informal definition for you to read over. And all this really means is a limit is something that as you get really close to an x value for a function, it means that your y values are getting really close to a single number. So a limit is like that boundary point for a certain x value. So we're going to talk more about that. And then something that's important to know is the notation that we use for limits. So the way that we write a limit in calculus is limit, or LIM, and then x approaching c goes right under the limit sign. Then we would write our function f of x, and then we say it's equal to our limit L. So we're going to use that notation throughout this when we're talking about limits and how to find them. So first, let's talk about something else that's really important. So all these words on your screen, all they mean for you is that a function can be undefined at a certain x value and still have a limit at that value. So say x is undefined at positive 2, the function can still have a limit at x equaling 2 as x approaches 2. So just because you're undefined doesn't mean you don't have a limit. So that's something important to keep in mind. So the first way we're going to find a limit is numerically. And to do this, we're going to show you how to do this with the example, the limit as x approaches 0 of sine x over x. So in this case, our c value is going to be equal to 0. So you see the table on your screen, and tables are really great to help you keep information organized. So you have everything written out really nice and neatly, and it's easy to see the pattern. So on a table, we're going to put our c value in the middle. So c is going to go right in this cell. So we're going to put a 0 there. And now if you notice, if we plug our 0 into the function sine x over x, we would get sine of 0, which is equal to 0 over 0. So we get something that's undefined. So in order to help us remember that we can't actually plug 0 in, we're going to put a big X in the f of x row under 0. So now what you want to do is you want to put in values that are really close to 0 on the left and really close to 0 on the right. So we're going to start down here in this last cell and work our way towards 0. And as we get closer and closer to 0 in the boxes, we want our numbers to also be closer and closer to 0. So what we're going to do is we're going to start off with negative 0.1 down here, negative 0.01, and then negative 0.001. So those are going to be our values to test to the left side of 0. And now for a full limit, you also have to test values to the right. So we're going to do the same thing. So it's going to start down here, and as we work our way closer to c from the right, our values are going to get closer and closer. So again, we're going to do 0.1, 0.01, and 0.001. So now this is where your calculator is going to come in really handy. So you can use your calculator to plug all of these 6 different values in, and then all you want to do is record the y value. So for this purpose, we're going to round to 4 decimal places. So when we plug in negative 0.1, we get positive 0.9983. For negative 0.01, we get positive 0.9998. And then for negative 0.001, rounding out to 4 decimal places actually makes the calculator round it all the way up to 1. So we're going to do that. And then now we're going to do the same thing for the right side. So starting down here, we again get, at 0.1, get 0.9983. Moving down, we get 0.9998, and then again we get the 1. So we can see as we approach 0 from the left this way, our y values are getting closer and closer to 1. Same thing from the right. So because those match up on both the left and the right side, we can say the limit for this is equal to 1. So that's how you find a limit numerically. So you can do the same thing for any other limit, just set up a table, plug in values, and see if your y values are getting closer and closer and more stable to a singular value. So the next thing we're going to do is look at how to find a limit graphically. So the word graphically has the word graph in it, so we're going to look at a picture. So we don't even know what this function is on your screen. It's just the graph of a piecewise function, but we can still use this picture to help us find limits. So what we're going to do first is we're going to look at function values of certain x values, and then we're going to look at the limits at those same values. So first we're going to find f of -2. Okay, so to do that we look at our graph, go over to -2, trace up to the solid dot, trace over, and it's at +3. So we could say that the function value at -2 is equal to 3. Okay, but now what about the limit as x approaches -2? So you see that notation popping up again. So now we need to find out what that is. So to do that, a great and easy way to always make sure that you're doing the same thing over and over and getting reliable results is to use your pen and just trace the graph. So to do this, first we're going to pick a point on the x-axis that's a little bit to the left of -2. So right here looks good. And then what you want to do is you want to trace either up or down until your pen is on the function. So in this case, we're going to go up. Okay, so now that we're on the function, all you want to do is follow the graph towards your c value of -2. So we're going to trace like this. Okay, so from that side, it looks like we're stopping at when y equals 2. So now we're going to do the same thing from the right. So now we're going to put our pen a little bit to the right on the x-axis, trace up to our function, and then follow the graph towards c equaling -2. Okay, when we do that, it looks like both of our red lines there are approaching the same y value at 2. So we'll say the limit as x approaches -2 is +2. Okay, so now let's do it again for a different x value. Let's look at at the function when x is equal to +1. So when we do that, we go over to +1, trace down to the solid dot, not the open dot, and we get that f of 1 is -1. And again, we're going to look at now what the limit does as x approaches -1. So we're going to do the same thing again. We're going to put our pen first a little bit to the left of +1 and then go down. So in this case, we go down because the function is below the x-axis. Once we hit our function, we draw another dot, and then we trace towards x equaling 1. So from that direction, it looks like we're going towards -1. So there we go. So now we're going to do the same thing from the right. So a little bit to the right, trace up to the function, and then follow the function down towards x equaling 1. But this time we stop at 0. So when something like this happens, when there's a break like there is right here between your two lines, and your pencil isn't going towards the same value from both the left and the right, we actually say that the limit does not exist. And the way we write that is we just write a big D-N-E to stand for does not exist. Okay, so let's look at one more function value before we move on. So let's look at f of +2. Okay, so same thing, we go to x equaling 2, go up to the function. It looks like we are over here at +2. So f of 2 is 2. And again, we're going to look at the limit. We're going to see what happens. So I'm doing this on the screen. Try and follow along and make sure that you know how to do it on your own. Okay, so again, we're going to start from the left, go up to the function, and follow it towards x equaling 2. So now before I do from the right, you guys kind of try and do it visually and make sure that you know what the limit is supposed to be before I say it. Okay, so now if we go from the right, again we're going to trace up, we're going to hit the function, follow it down. So it looks like we're actually hitting our limit at 2. So the limit at 2 is also 2. So this is a really great picture for a lot of reasons. It shows you how to find the limit graphically, which is a really great skill to have, and it also illustrates some different points. So you'll see up here at -2, we had a function value. So the function's defined at -2, and its f of -2 is 3. But if you look at the limit's not equal to 3. So the limit and the function value, they don't have to coincide. They don't have to be the same number. They can be different, just as you saw here. And then we have cases like at x equaling 1 where we are defined, we have a y value of -1, but we don't have a limit. So just like I was saying earlier, if you're undefined at a value, you can still have a limit. You can be defined at a value and not have a limit. So you really can't just say, hey, I have a y value, I have a limit, because you might not always be right. And this would be a perfect example. And then down here we have another thing that can happen with limits where your y values and your limits of the function match up. So they can be the same number. They're not always going to be different. So another important thing to talk about before we end for today is what happens if a limit doesn't exist? Why doesn't it exist? And what are some cases when I'm going to see this? So there's three important things that you need to look for to see if a limit does not exist. One case when it's not going to exist is if your function is approaching different numbers from either side of your c value, which is exactly what happened at x equaling 1 in our last example. Because from the left we were approaching -1, but from the right we were approaching 0. So two different values, no limit. A second case is if your function is blowing up to positive infinity or down to negative infinity. Because infinity isn't a number, it's a concept, we can't say that there's a limit there because our function isn't approaching a single value. It's approaching infinity, which isn't a value at all. So in that case, we're also going to say that the limit doesn't exist. A great example of this is if you look here at a quick drawing of f of x equaling 1 over x squared. If you look here around 0, you can see that from both the left and the right, as we get closer and closer to 0, we're blowing up straight to infinity. So because we're not approaching a number, that would be a reason that the limit doesn't exist. And a third case for when the limit doesn't exist is if your function oscillates between two different values. And that just means that your function is jumping up and down a lot. So trig functions are a great example of this. So like if we look at the function f of x equaling the sine of 1 over x, we get a graph that kind of looks like this. We're just going to draw around 0. So around 0 you get like this. Now that's a really rough picture, but you can kind of see what's going on. And in here, it's jumping up even faster than I'm showing. If you look at it on a graphing calculator, you'll see it looks like this big mess in here. And so as you get closer and closer to 0 on both sides, you're going to jump up and down. And you're not going to be stable around a certain value. So because of that, you can't say that you have a limit. Okay, so I hope this helped clarify some things about limits for you. And in the next video, we're going to talk about how to use different algebra methods and different properties of limits to find what the limit value is for functions. Okay, have a great day.